Okay, hello to everybody. Today the first speaker is Thomas Weber from Bologna, and he will talk about principal differential calculi on quantum Flach manifolds. Please.
Thank you. So first, let me thank Piotr, Tomak, and Soren for setting up this nice conference at this really beautiful place, and also for letting me give a talk here, even though I'm definitely not an expert on graph algebras. In fact, I will not even talk about C-star algebras. I will take a step back and look at the Hopf algebra level, look at their actions or co-actions on algebras, and see what kind of differential calculi we can build there on this level. But it will turn out that some of our toy models are actually connected to the graph algebras. So maybe let's see if we can also learn something from this graph language. Okay, I should say that this talk is based on joint work with Paulo, Rita, and Emma. And so let's start. Okay, the plan of the talk is twofold. So I have a fine part and then afterwards a sheaf part. So let me build up a little bit on this. So my structure group will always be a Hopf algebra here with a coproduct delta, a co-unit epsilon, and an antipode S. And my space, so my quantum space I'm looking at will be a right-H co-module algebra A. So this just means I have an algebra, I have a Hopf algebra coaction on A, and I would like that the coaction is an algebra map. So there's a first problem, if you want to call it problem, that while in differential geometry, there's a God-given calculus. In quantum geometry, we have many. Yeah, there are many possible differential calculi on A. So it's a question you might ask, what is a good choice? And you can see this as a problem or as a feature. In a sense, it's even nice to have more freedom to choose your differential structure. And one way to think of a good choice is I will try to tell you on the level of Hopf-Galois extensions. So a Hopf-Galois extension is written here. The definition will come on the next slide. You can think of this as a quantum version of a principal bundle. And what we're going to see is that on those bundles, we can find differential calculi such that we get a graded quantum principal bundle. You will get a graded Hopf-Galois extension here. And so this will lead us to the notion of a principal covariant calculus. And those will be calculi satisfying this kind of sequence here, where you have horizontal forms into vertical forms. Yeah. Okay, this is the first part. For the second part, we will look at this following problem. So usual in quantum differential geometry, we don't have an underlying topological space. We just view algebras and modules as, let's say, global functions or sections. So what are we going to do if, let's say, we don't have very many global sections? And see here we can look at CP1, and we look at holomorphic functions there, where of course we have just constant ones, so only trivial global functions, but we have non-trivial local data. So what is a good way to quantize this space? And then on the nose answer is, okay, just work with quantum ringed spaces where you have a classical topological space here, and you have a sheaf of algebras. And okay, just wrote out what this means in the CP1 case. So globally, you have just a constant functions, but locally, you have some non-trivial parts. And so yeah, the point is here that we should try to understand those kind of examples rather as so as sheaves rather than as just global functions. So this will then lead us to the study of sheaves of co-module algebras that have some local property. So let's say on an open cover or on stalks, maybe we want some Hopf-Galois property, or in the case of differential calculi, we would like that locally they form calculi, blah, blah, blah. So we will see this later. So the point is, okay, some global to local properties will come in the second part. And the main class of examples that we are going to look at, we have seen partially in previous talks. This will be this Q deformations of complex semi-simple Lie groups. Here we are going to look at them with a parabolic subgroup. And this will need the notion of OR extensions. Okay, and as I mentioned, some of our key examples like SUQ2, the Podlesh sphere, and CP1, they will feature graph algebras. So
here by Podlesh sphere, I mean this equatorial one, generic, right?
And yeah, so just some open questions that since we had a graph algebra.
Wait, isn't Q missing from the last O?
So here you don't really see the Qs, as you can see in this sheaf here, everything is commutative. So you don't have, so this will only be visible for the higher ones.
But I'm confused. I mean, the standard Polish quantum sphere is CP1Q.
Sorry, so here Podlesh will be this here. So the CP1 will be this sheaf here. So I don't take the global functions, I take the holomorphic functions that have to be.
So your first previous answer was wrong. You meant standard Polish quantum sphere by OQS2. Which algebra do you mean? With one character or the circle?
So this one here as a graph algebra is the one with infinite vertices.
Yeah, so that's standard, not
edges. Sorry,
yeah. Okay.
Okay. Hopefully it's clear now. So then, yeah, some open questions. Just during this conference, I was also wondering, maybe one could think about differential calculi on graph algebras, and maybe they are also given in terms of graphs, something like this. And okay, the second question here, since many of the examples will be in terms of graph algebras, maybe one could even learn something about quantum principal bundles from the language of graph algebras.
May I answer the second question?
Please.
So it happens, like, for instance, in the case of this Podlesh quantum Hopf vibration, so SUQ2 over S2Q of Podlesh, the standard one, then there's U1 action with which Podlesh defined or got his sphere. That's exactly the gauge action on the graph. Okay. And it goes to higher dimension, Waxman-Sobelman, Waxman-Sobelman spin Q. So, but these are only circle bundles. Okay, but we're actually quite lucky because under some mild assumptions on graphs, the gauge action is free. So you have a compact quantum principal bundle.
Okay.
But I know about calculi. Elmar, what do you think?
Classical algebras, you have not differentiable functions. So it's very difficult to get smooth functions from a classical algebra.
Okay. Let's see. So let's start with the talk. So yeah, one of my main definitions you can see here is that of a Hopf-Galois extension. I will always work over a field K, and H will always be a Hopf algebra with coproduct written here, co-unit this one, and antipode S, which for me S will always be an invertible function. And we are going to use Sweetler's notation for the coproduct. So here we know this maps into a finite sum, but we are lazy, so we just write H1 times H2.
I also dropped parentheses.
There are several different versions of how to do this, and the most lazy one is this one. Yeah. So I stick to the most lazy one.
I agree.
Well, the most lazy one, you don't even write 1 and 2, it's just H tensor H.
But this,
Yeah, that's the most lazy.
One is
right.
the first entry and then the others.
But this looks then very group-like, so you should be careful. Yeah. Okay. So, yeah. Let's see. We can be very lazy and not even write anything. So very good. So A will be a right H commodule algebra with right H coaction delta A. So this is a map from A into A tensor H. And as I said, this is a coaction and an algebra morphism. Just written here what an algebra morphism is. And also for this coaction, we take some kind of Sweetler notation here with 0 and 1, where the 0 tells you what is the A part. So giving this data, we can look at the Hopf kernel or at the co-invariant elements B. So this will be the subspace of A, consisting of the elements that are not changed by the coaction. And it's easy to see that this will give you a subalgebra of A. So then, Piotr, maybe you can help me if this is the first reference here, but
that's a standard citation, yes.
Okay, it's the
yes.
standard one.
It's like, in organic geometry, it's cite Comprandi note about quantum torus in 1980. So that's been Hopf-Galois.
Okay. So I would cite this one here at this talk. And so just the definition of what it means to be Hopf-Galois. So you take B and A, as we have seen. And so there's a canonical map here. And in case this this map is a bijection, we call B and A Hopf-Galois extension. So just have a quick look at this map. It is just so if you take something in a balanced tensor product, you coact on A prime and you multiply the A parts. And that's helpful. Let's quickly go through some examples. So maybe the easiest one is if you take A equals H. In this case, the invariants under the coaction are just constant multiples of the unit. And you can give and the inverse of the canonical map via the antipode. So see that this works. The next crucial example is from differential geometry, where we take a G principal bundle. Here A will be functions on the total space, H functions on the structure Lie group. And okay, we have a right G action. And the pullback of this action will give you a coaction. Of course, here I'm a little bit sloppy because you have to complete things in the Frechet topology, sorry, because otherwise this doesn't make sense. Yeah, and then you can show that the functions or the functions that are invariant under this coaction, they correspond to functions on the base manifold. Furthermore, you have from
Sorry, by this tensor product, you mean the tensor product of Frechet algebras?
Yes. Yes, from differential geometry, we have this map here into the fiber product, and you can see that the pullback of this map will exactly give you the canonical map we have seen on the previous page. And then it's not hard to show that chi is really a bijection in case R is free and if it acts transitive on fibers. So this is also the motivation why Hopf-Galois extensions are called quantum principal bundles, quantum versions of this example here. Okay, the next one, next example, sorry, will also be crucial. So it's SLQ2, which is very similar to SUQ2. I mean, that's just SUQ2 is just a real form of this one here. So I will give the definition, even though we have basically seen it many times throughout this conference. So this is the free algebra generated by some alpha, beta, gamma, delta, and then we mod out some commutation relations that are written here, the Manin ones, and the last one is the quantum determinant, this one here. You can show that it is a Hopf algebra with the coproduct written here in matrix co-multiplication. So we have also seen what this means. So for example, a delta A, a delta alpha will just be alpha tensor alpha plus beta tensor gamma. That's really just matrix co-multiplication. I don't even write a antipode, but it's done in a similar way. Okay, on this space, you have a U1 coaction, and this can be written in a nice way using the following projection of algebras, where we just map the generators into here, t and t minus 1. And okay, then the coaction I was mentioning is just the coproduct on A, where we project the second tensor factor. Okay, it turns out that we have basically also seen this in the conference, that the invariants under this coaction are exactly the Podlesh sphere. And one can show that this is a faithfully flat Hopf-Galois extension. I didn't mention faithful flatness yet, but we are going to see this in one of the next slides.
Before you change slides, may I have a quick comment?
Yes.
If you look at this formula for phi, and you see that immediately by construction, it's subjective. Okay, it's basically the images with fiber product. So you'd expect that until you do the pullback, things should be automatically injected. It's not quite the case. However, we have one of the most fundamental and beautiful theorems in Hopf-Galois theory due to Schneider, and he proves exactly under your last assumption of faithful flatness, which is tantamount to principality and the existence of a strong connection. He proves that indeed subjectivity implies injectivity. So like in the classical case, what should be given for granted is given for granted, but under this additional assumption of faithful flatness, which is always satisfied whenever you come from compact quantum groups, because when your Hopf algebras are quasi-simple, you have this Haar measure, and everything works automatically. Everything is always faithfully flat.
Great. Thanks for this comment. Later on, we will actually going to see Schneider Theorem. So this is even part of the talk. Very good. So this is just the graph picture of the last example that I showed. I mean, I was mentioning that SUQ2 is a real form of pointer doesn't work. So of SUQ2. And okay, so the graph picture of this quantum principal bundle is this picture here. And I don't know if we can learn something from that. Let's see. So
well, we have lots of theorems about gauge actions, so
that I have to learn first before giving a talk about it. Absolutely. Good. So let's come to Schneider theorem. Exactly, this is what's going to happen. So the next thing is we don't only want Hopf-Galois, we want also faithful flatness. That's a assumption that we are going to need later on. And so we call a faithful flat Hopf-Galois extension a principal comodule algebra. And just one word, one sentence on faithful flatness. So A is faithfully flat. Let's say as a right B module. If you look at this functor here, that I will tell you in a moment what it means, and this has to be an exact functor which reflects exactness. So what does this functor do? It's from left B modules into Hopf modules. Hopf module means you have a left A action and a right H coaction, and they are compatible in the sense that the coaction is left A linear. What does the functor do? It takes a left B module and maps it into this module here. That is then a Hopf module with action and coaction, just the ones on A. It does a functor the other way around. It takes a Hopf module and maps it into a left B module, by just taking the co-invariance of this module. And then, as Piotr was mentioning, this Schneider theorem, very deep, very interesting theorem that classifies these principal comodule algebras. And Schneider says, so A is a principal comodule algebra if and only if you have a categorical equivalence here of the left B modules and the Hopf modules. So this means that if I apply the two functors, I will get something that is isomorphic to the module that I started with. Similarly, other way around. We are going to use this later. Examples are SLQ2 with U1 coaction, as we have seen on the previous slide. And one more class that is kind of interesting is every cross product algebra automatically gives a faithfully flat Hopf-Galois extension. So I don't give you the definition of what this is, but so here this just uses some version of a twisted 2 co-cycle with values in B, and then you take a crossed product here, which corresponds to the cleft of Galois X tension. So here we have some kind of cleaving map that is even more structure. Those of Galois X tensions are sometimes called with the normal basis property. Yeah, since you have this composition, decomposition. Okay, so this was the first part. Let's say, or yeah, the first part of the first part. Let's come to the differential calculi. So just a very basic slide. In principle, here we just need an algebra, but since later on everything will have a coaction, let's do it for co-module algebras. So this definition probably goes back to Vodonovich, I would say. There's of course also early work of Hon, but maybe for this definition I would cite Vodonovich. Very nice paper of 89. So he says that given A, we call a tuple gamma D a first order differential calculus on A if those 3 properties are satisfied. First one saying gamma has to be an A bimodule. Second one, D is a linear map from A to gamma that satisfies the Leibniz rule. And here you can see that we really need a bimodule, otherwise this definition doesn't make sense. And the third property, we would like every element of gamma to so that we can write every element of gamma as a finite sum of A dB. So this is sometimes called the surjectivity property. So this is what a first order differential calculus is. Now, what is a covariant calculus? Yeah, we have this extra coaction, and we would like the coaction to lift the level of differential forms. So a first order differential calculus on A is the right H covariant if it's a hop bimodule. So we have seen those hop modules here, but here we also have a right A action. We also would like this A action to be compatible with the H coaction. And of course, we would like D to be right H collinear, so also compatible with the coaction. Examples are, of course, the classical case. This is the sanity check. So if you don't get the classical case, you're doing something wrong. So if you have a smooth manifold, you take as gamma the sections of the cotangent bundle. Then you take the RAM differential. And let's say just a Lie group action on your manifold, you take the pullback of this action and you're getting a covariant calculus. Second example, a very crucial one, is the universal calculus. So this works for any algebra even. You just take the kernel of the multiplication of your algebra, which you can multiply from left and right. And you take as universal differential this map here that takes A and maps it into 1 tensor A minus A tensor 1, which you can easily see lands in the kernel, right? If you multiply, you get 0. And what is nice about this calculus is you can show that every calculus is a quotient of this calculus. So this is kind of the biggest choice. Right?
A slight objection to your example number 1, because when you go commutative, you get this scalar differentials, not the RAM. And the issue of the algebraic tensor product versus this Frechet tensor product is not a minor one, a serious one. So yes. You're kind of brushing under the carpet a non-trivial identification, and it's not the same thing.
This is true. So here I'm kind of sloppy, and yes. So let's see. My background is in deformation quantization, so I always would like to have the smooth setting as a special case. That's why I write everything smooth. Okay, so for this universal calculus, I said every other calculus is a quotient of this one. So this is a kind of maximal choice. Or if you want to say it in a different way, so the first order differential calculi form a monoidal category, and the universal calculus is the terminal object in this category. Okay. So a quick slide about base and horizontal forms. So now let's take a principal co-module algebra. So yeah, this was a faithful flat top-Galois extension. And in this setting, we have a good notion of what are base forms and horizontal forms. So let's start with a right-edge covariant calculus on A. Recall that this means that the coaction on gamma is A bilinear in this sense here. And then we make the following definition of base forms. We just say that this is kind of the pullback calculus. We can see B as a subalgebra on A. So we just take the elements that are spanned via B. And it turns out that this is it's very easy to show that it's a differential calculus, with the differential simply being the restriction of the differential on A. Furthermore, we have this notion of horizontal forms, which is just the left A module generated by gamma B. Let me say that here there are different conventions. We will say that we will see that some people here take actually the A bi module, so A on both sides, but we would like the left A module. Some proposition that you can prove is that base forms are characterized as the horizontal forms that are also co-invariant. And I mean, I have to prove here, we don't have to go through it. This is just to say that the proof is easy. And I just want to point out that here in this proof, we are using several times Schneider Theorem. For example, you can look here. So this ISO is exactly Schneider Theorem. And also here we can look at it. That's maybe what you should take from this proposition, that here this faithful flatness is really crucial in order to prove this proposition. Okay, the next thing is a principal covariant calculus. Okay, so we still have a principal comodule algebra. We take a right-edge covariant calculus on A and a bi-covariant calculus on H. What is this? So on H, of course, we have two canonical H coactions on H, just given by the coproduct. And for a calculus on H, we would like those coactions to also lift to the level of forms. And this is what is called a bi-covariant calculus. There's a nice classification theorem by Voronovich. So we always know that there are some calculi. We can always choose some. Given this data, so those two calculi, we call the combination of those two calculi a principal covariant calculus. If we have a certain vertical map, we are going to see what this is in a second, and an exact sequence here. So let's understand the sequence first. So here, this arrow is just the left A module action on gamma B. And this here is the cotensor product, which we have probably also seen once or twice in this conference. So here just is the definition. It's kind of the dual definition to the balanced tensor product. So what about this vertical map? So the vertical map goes from gamma into the cotensor product. And we know that we can write any element of gamma in this form here, a finite sum actually. And then we would like the vertical map to first coact on A and A prime. So this is the A0 and A1 and A prime 0 and A prime 1. And so we get something in A here that we can multiply. We get two parts in H where we apply the differential. So this will now be something in gamma H. The problem is this map doesn't always make sense. So you have to make sure that this is a well-defined map. And if it is, and if you have an exact sequence here, we call our calculi a principal covariant calculus. Examples of this one, you will see on the next slide, will be the three-dimensional calculus on SLQ2, which is seen as a principal comodule algebra with the Podlesh sphere and the U1 coaction. And let me just mention that if you take the 4D calculus, so this is saying, yeah, on the first slide, I told you that there are many choices. And so here on SLQ2, we have a 3D calculus, also a 4D calculus. And it turns out that the 4D calculus is kind of too big. So here you won't get exactness of the sequence, which might tell you that the 3D calculus is a better choice here. Okay, so here we don't have to go through all of this slide, but just very briefly. So here I just want to show you what is this 3D calculus on SLQ2. So gamma, the one forms, they are a 3 left A module generated by a basis, so 3 elements that are called E minus, E plus, and E0. You have some commutation relations. It's not very crucial to understand them exactly. It's just you basically get some Q to some power. And the differential is written in terms of this basis in this way here. You can show it's a right age covariant calculus. On B, you take the pullback calculus, via this inclusion here. And on H, you take the quotient calculus. So this is possible because you're having a projection map from A to H here. That's why you can take a kind of quotient calculus on H. And you can show that the vertical map is very easy in this case, and that it makes the sequence exact. Just very briefly on the 3D calculus. Some comments on the definition of a principal covariant calculus. We are not the first people to do this. There's a much older story about strong quantum principal bundles. And I mentioned at least 3 names here, Piotr being one of them. So there's a very similar sequence that I wrote here that one can show that in the faithfully flat case is the same as ours. So those two notions coincide. Okay, but so as far as I know, we were the first to prove this theorem here. So this is kind of the first question that I was hinting on my first slide. So we have this theorem here. Take a principal covariant calculus on A with a bi-covariant calculus on H. And then you get a faithfully flat Hopf-Galois extension of graded algebras. Here the smaller equal 1 means this is the truncated in the degree 2. So we have just 0 and 1. So here we get a graded Hopf-Galois extension. And even more, you get that the coaction on A is a differentiable map, which just means that you have commutativity of this diagram here. Okay, and it's even more. So this statement is a kind of if and only if. So it says that, let's say you have a faithfully flat graded Hopf-Galois extension here, such that this is a commutative diagram. Then you find that gamma D has to be a principal covariant calculus. So this really is yet one more classification of what does it mean to be a principal covariant calculus. Good. So for the proof, I mean, I just hint here a little bit on how this is done, maybe also clarifying how you get these graded actions, these graded coactions. So how do we, so for this to be graded Hopf-Galois, what we need is, let's say first, that this here is a Hopf algebra. How do we see the H plus gamma H as a Hopf algebra? That's written here. So you take the usual coproduct on H, but on gamma H, you take this map here. So the sum of the right and left coaction, which is now a map from gamma H into gamma H tensor H plus gamma H. So you can really see this is a degree 1 map. And also the antipode on H is the usual antipode, but on 1 forms, it is like this. So you take a 1 form omega and you map it into this expression here, which means you left coact and right coact. You apply the antipode, you multiply, and there's a minus sign that you need here. And you can show that this is a graded Hopf algebra. In a similar way, for A, you take this direct sum here with the usual coaction on A, but with the coaction on gamma, now given as the sum of the right coaction plus the vertical map. And this is kind of nice that here in this graded coaction, the vertical map appears. You see it's a map here. Anyway, and then you can show that that omega smaller equal 1 on B is really the space of invariance under this graded coaction. And the proof is written here. It's not very difficult. So this lemma you are using to prove one of these main theorems.
I have a question.
Please.
What are algebraic properties of this map delta 1A? Is there some kind of infinitesimal coaction? What is this?
So if you have a graded coaction, you just look at the first degree map, and
Yes, if you
are
have.
going to figure out what are the properties. Yeah, so it's
So can you complete it to some coaction which is coassociative and counital?
so it is a coaction if you use the delta 0a. So if you take delta 0a plus delta 1a, this is a coaction on this space here. This is the statement of the lemma. And if you want to see higher orders, I mean, you can try to do this, but here I truncate, so I just look at 0 and 1.
Yeah, but my question is, what does coact on it?
So the Hopf algebra that coacts is this one here.
It's a direct.
And the one below A plus gamma is the comodule.
In which sense it's a graded Hopf algebra?
Okay, so let me rephrase this. So first, maybe I can give it a algebra structure. I was hiding this. Yeah. So so how do you multiply here? Yeah. So let's say
Gamma H is a square zero idea.
exactly. So if you multiply one form, so you get 0. If you multiply a 0 form with a 1 form, it's just a module action, and okay, functions are multiplied as well. So this is
the usual way you transform a bimodule in algebra and a bimodule in a graded algebra.
And how about your antipode as 1? Is it obvious that it's again bijective, or you don't care?
a very good question. I don't know. I've never thought about it.
Okay.
Yes. It's a good question, but I would guess.
I
that
guess
it
it's
is,
bijective, but
I would guess so, but one has to prove it.
I can assign it as homework.
I will do that. Yeah, maybe on the train. Yeah. Very good. So if this answered the question, then let's go to the next slide. So this now finishes the first part, which was the affine part, let's say. Now let's go to sheaves. So as we have seen, it might be good to have a similar framework also on the level of sheaves, because in some cases the global sections don't have all the information that we need. So here, just very briefly, what is a sheaf of comodular algebras? Take a classical topological space M and a Hopf algebra H. Then we say that F is a sheaf of right H comodular algebras if all of those properties are satisfied. I mean, I'm not going through it. I think probably all of you know what a sheaf is, but it's just okay. For every open, you get a right H comodule algebra. You have some restriction morphisms that have to be morphisms of comodule algebras with the usual compatibility. You have some property that says it's local and that you can glue. Really just the usual definition of a sheaf. So let's take a quantum ringed space that is just a topological space M and a sheaf of algebras OM.
There's a little terminological problem, associativity of these words. Okay, because in your definition, quantum ringed space, this ringed part is quantum. Quantum ringed. So maybe this should be with a hyphen, quantum ringed. But the space part is classical.
It's classical, absolutely. Yeah. So I mean, I said it in words, but maybe the terminology can be a little bit confusing. So it's M is really a classical topological space, and I just have a sheaf of any algebra. I mean, I don't have necessarily commutativity here.
I think you just put hyphen, or you call them spaces that are quantum ringed, and you switch.
I have to say that it was not me coming up with this name. So this is an old
Who
story.
introduced this?
I don't
Who
know.
introduced this?
So I'm not sure who was the first one. So I learned this from Rita, but I'm pretty sure the story is much, much older. So
Because people were talking about spaces ringed in non-commutative algebra with non-commutative algebra sheaves of non-commutative algebras for ages. The category D modules, if you have a manifold and you have a sheaf of differential operators, it's of this sort. But they didn't use word quantum.
So this I fully blame on someone else. It's not my wording. Yeah.
I wanted to know who is guilty.
Let's blame Rita. Okay.
Which is probably online listening.
Very good. So with this, yes. So this definition of okay. Also here, one more maybe problematic word is so those sheaves. They are sometimes called quantum principal bundles. While we have seen that quantum principal bundle also applies to the Hopf-Galois, right? So here we say that a quantum principal bundle on a quantum ringed space is a sheaf F of right H commutative algebras that is locally a faithfully flat Hopf-Galois extension. So let me explain. So this first axiom means that, so take an open cover of your space M. Then you would like to have that on this open cover, the invariants under the coaction of F are exactly the algebra on M. And furthermore, that on this open cover, you have principal comodular algebras. So faithfully flat Hopf-Galois extensions. Good. Let's see. I guess I have to speed up a little bit, but maybe, yeah, we don't finish everything. So let's see. So let's look at SLQ2 now over CP1. So how does this go? So we take as in the previous slides A as OQ SL2, but now not with the U1 coaction, but with the parabolic coaction. Sorry. So how to CP? So this is maybe best seen via this projection here. So you go from SLQ2 into OQP in this way here. You take the upper triangular matrices as an algebra. Here are the Porte quotient avatar. This is how it looks like. And now we would like to see this as a quantum principal bundle on the sheaf level. So we need an open cover and then prove that those two properties are satisfied. And for this, we are taking a very coarse topological space. So we take CP1 with just 5, if I counted correctly, opens. So we take the empty set, we take the full set, we take the upper hemisphere, the lower hemisphere, and the intersection of both. And then on this, okay, maybe here, now I can draw. So here we build a sheaf in this way. So globally, we take the we take all the functions on SLQ2. Then on the open U1, we take the OR extension of this algebra, where we allow alpha.
So
to
U1
be
is not the hemisphere, it's that sphere minus 1 point, right?
Yes. Yeah. Okay, I shouldn't say upper hemisphere, so it's minus 1 point. Okay, on U2, we take the other extension. So let's take the OR extension where we allow gamma to be an invertible element. And on the intersection of both, so on U12, we take both functions. So A with alpha -1 and gamma -1. And you can see that, yeah, you have injective arrows here. Good. So, and for proving that this is
by adjoining the inverse of alpha or gamma, you mean a localization.
So this is the, yes, I localize, yes.
But it's these elements are not central. So this means you are talking about what? Or a localization.
Yes.
So you have to check that this satisfies this OR condition.
Yes, and they do.
They do.
Yes.
Okay.
Very well. And furthermore, you can prove that this is actually a sheaf. So you have to, so here it's very easy since you have not many opens. You have to check that you glue in the right way. So let's say that you have a function here and a function here, which coincide here. Then you have to check that they actually come from a function here. Yeah, and this is kind of easy because you can see that if you would have an alpha -1 here or a gamma -1 here, what you get here will never coincide. So it has to be something in A. And okay, this is how you check that this is a sheaf. In a similar way, you do it on CP1. So let me also draw the picture for CP1. So globally,
Sorry, I have a question about this F of U12. U12.
yes.
Okay. So first you are inverting alpha, and next you have to check the OR condition for gamma, but inside of this localized already A with respect to alpha.
Absolutely. And
everything works.
yes, and
So this is a secondary, yeah. But you could do a symmetric thing. First invert gamma and next alpha. Is this the result the same?
very good question. So yes. So this is what we checked, that here it doesn't matter what you do first. I mean, if you first invert alpha or gamma, it gives the same algebra.
What you mean? This isomorphic algebra.
Isomorphic algebra, yeah, this is the same in the sense that isomorphic, true. Yeah. So this makes sense. Okay, so the picture for CP1. So globally, we were saying we just have the constant functions. So on the first open U1.
Sorry, let's to say that the same isomorphic algebra. You need also some universal property.
So this follows from the OR property, yeah?
Yeah. So
which is a universal property.
This the problem with isomorphic to algebra, because using universal properties of OR localization in one order and in second order. Okay. I don't know what is the. Okay, I don't understand what is this. So it's a pair of mutually inverse maps from one to another using the universal property of OR.
So you're asking how to prove?
Yeah, I have a problem with this iterated OR condition. Okay, because playing with this iteration and using this universal property of OR localization.
But maybe this is a question for the coffee break because you need to write on the blackboard.
We can talk about this
so please,
later.
Please
but
remember my question for the coffee.
Yes, but maybe here I can just say that. Maybe here I can just say
I could forget.
Keep in. Let me just comment quickly here. So keep in mind that SLQ2 is a very easy, very small algebra. So here things can be checked in a very explicit way. So just as a comment. Okay, so just since we are running quite a bit out of time, so let's see this sheaf for CP1. Globally, we have just the constant functions on U1. We have now one generator. So we have CQ of some variable u. On u2, we have some v, and on the intersection, so see it, it's a CQ of, let's say, u and u minus 1. And then here, as the restriction morphism, you just have to map v into u minus 1. And you again check that this gives you a sheaf. And I mean, it's furthermore, you can see that the invariants under the parabolic coactions on this algebra here are exactly those algebras here, those elements here, if you understand u as the element alpha minus 1 gamma. And in a similar way here, what the invariants of this algebra are exactly those if you understand v as gamma minus 1 alpha. And you can see that on A. So globally, you have only the trivial ones. So you don't have any non-trivial invariant functions. Good. And so this is just showing that this is a sheaf and that on even any open, you get the correct invariant functions. Furthermore, this is a quantum principal bundle. So you have this Hopf-Galois property, faithful flat, because you can find cleaving maps. And here I just sketched that, okay, those are the cleaving maps, you can write them down. So you get on the nose a faithfully flat Hopf-Galois extension locally.
Plus minus is plus minus 1.
Plus minus is plus minus 1? I don't understand.
I don't understand the plus minus. What?
Ah, sorry. So here, so the J maps, they are from H into A, yeah, H into A, and the generators of H are here. So we have, okay, so for T, I write T plus. Like, it's just a short way of writing both. Yeah, I don't have enough space here. I don't want to have an overload of formula. T plus is just T. Yes. So,
yeah. So it's plus minus 1.
Okay. Sorry. It's so standing here. It's very hard to comprehend language. Yeah, I'm sorry. So let's go to the next slide. Let's see. So in the last 5 minutes, maybe I can just yeah, come to this one theorem and then I skip the rest. So so yes, one of the main class that also includes this previous one here is for the complex semi-simple algebraic groups and their Q deformations. And so here's just one slide kind of saying how to build the sheaves for those guys. So let's start. I mean, this is a little bit technical, but bear with me. I try to make it understandable. So take a complex semi-simple algebraic group, take a closed algebraic subgroup. Usually we take parabolic subgroup, take a character on P. And then we would like to have a line bundle on the quotient associated with this character, such that you have the following global section. So you take the functions from G to C that are linear under the right P action in this way. So G is in G, H is in P, and you can, so it's linear in the sense that you can pull out the H under this chi minus 1. Then we would also like to have that L is ample and gives a projective embedding of GP. In this case, we define here the coordinate ring as this sum that will turn out to be a direct sum with the n parts in this way. So here it's the same as we have seen here, just that we have the n negative power of the character.
Sorry, so in the classical version of the previous example, this projective embedding would be identity.
So let's see. So in the example before, we would have the character that would map to the determinant.
To the top left element. Maybe.
The top left element, yes, this could be. Yeah. So okay, and let's try to understand this in a Hopf algebra language, since I mean I'm more into Hopf algebra, so I have to see co-products and antipodes, otherwise I don't understand things. So what are we doing here? So this chi corresponds to an element of OG, which has some properties. So if we take the co-product on it and then project, this is very much like a group-like element. Okay, you have that pi sm shouldn't be the same as pi sn. We have m different from n. And so this condition here can then be written in Hopf algebra language in this way. So take an element of OG, you take the co-product, you project on the second tensor factor, and you get this here f with pi s to the power n. This is here the nth part. And okay, this is what is sometimes called a classical section of the line bundle L of the quotient space.
And in the previous example of SLQ2, what would it be?
Yes, so here the quantum section is just alpha in the previous
okay,
one,
thank
alpha.
you. Yes.
This I'm sure about.
Yeah.
Okay, so there's a theorem, yes, by 3 authors, including Rita, that have a quantum version of this classical section, which is like this. So now you take an here I'm a little bit fast. So here now there's a Q. So now we take a Q deformation of the previous algebra, and here I mean we've seen this in previous talks. So you basically take the corresponding Drinfeld-Jimbo quantum group, and the dual of this one will give you a quantization of your coordinate ring. So this is, I mean, but you also could take something slightly more general, but let's think about these Drinfeld-Jimbo quantum groups. And okay, the properties of this quantum section SQ should now, so this this group-like one should be the same as for the classical section, but you would like that the limit when Q goes to 1 should give you a classical section of your bundle. It's a deformation, yes. Deformation of the classical section. That's it. Exactly. And in this case, you can define these deformation of the quotient space with a sum here that will turn out to, so we can prove it's actually a direct sum. Yes, in this way. So just the same definition, just with the quantum section. And they show that this gives you a projective homogeneous quantum variety. Furthermore, if you take the classical section S, and then you can write the co-product of this classical section in a certain way. So you have a finite sum here. You take the set of elements here, and they give you magically an open cover of the quotient space. So now take the finite intersections of those open covers, and this we call U capital I, where I is now a multi-index with a lot of indices. What has been shown that using this open cover, you can now build sheaves on the quotient space and on OQG. And I mean, I'm almost out of time. Let's see. So just very briefly. So on the base space, what you do is you're using combinations of the inverse, so in the OR sense of the quantum sections with elements of the quantum section. And on the total space, you also take the OR extension, very much like we have seen in this toy example here. And okay, you can show that the invariance of the total space sheaf give you exactly the base space. And for the special case, if you take SL n+1, you can show that this is even more, that this is a quantum principal bundle. So in this case, we can also find the cleaving maps, and we can show that this extension is Hopf-Galois. Okay, I'm really out of time, so maybe just not sure it makes sense. So, okay, we have also a definition of what is a differential calculus on this sheaf setting. And just the take-home message is you take sheaves where you just ask locally, in the sense of on stalks, that it's a differential calculus. So you have like Leibniz rules and this surjectivity property just on stalks. And we could prove a theorem that is very similar to the one we have just seen. So if you take this Q deformations of your spaces and the corresponding sheaves FG and OM that we have just seen, then we can also build differential calculi on those sheaves in a nice way. So this is like the differential calculus analog of the previous theorem. And I'm sorry for going over time. I stop here. Thank you.
Are there questions? Yes.
Hello? Okay, good.
Yes.
Yes. So for sheaf, so it was basically a covariant functor from the category of open sets, right? Of say CP1 to the category of these H comodules. But it should be all the open sets of CP1 in your example. Like you gave us a finite list, the set like a right. What about other open sets?
Yes.
Or you do not care?
Yes. So thank you. That's a very good question. So the point here was kind of saying that here I'm happy with a very coarse topological space. So I'm happy just taking very few opens. I don't want all of them. And that's I know maybe you can think of this as kind of the quantum philosophic way that you are even fine with just taking a finite amount of opens, and you can build some interesting models just on those very few opens. But you are correct. I didn't give you any definitions here with infinitely many opens.
And then you talk about stocks. So then it's like a stock means that you are shrinking your open sets, right? So to the point. So,
also, very good question. So I didn't have time to talk about this more. So the nice thing is, so if you have a finite topological space, then the stalks are just the minimal opens. So you think of, if you take a point, yeah, then you just take the maximal intersection of all opens, and this will be your, so yeah, this, so the algebra on this maximal intersection is the same as the stalk of this sheet.
So okay, the stocks means that you, so in the sum of slides, and then you choose a open cover, right? So then you sort of use this open cover to generate this the category of open sets. And
absolutely, absolutely.
Okay.
And so this open cover, that's also crucial. I mean, this I mentioned briefly, corresponds to this quantum section, right? So you have the co-product on the quantum section, and one of the legs kind of gives you on the nose what is this finite open cover.
Yeah. Okay. So, but here you are using the usual smooth topology. Can you use these the Zariski topology like in algebraic geometry? Just random question.
I didn't think about it. So
Subtopology of the Zariski topology.
The one in the example, you mean?
Yeah, in this example. I have a question, because for richer topologies, the shift condition is more demanding. It's a uniqueness of gluing, in a sense. Not every pre-sheaf satisfies this. But if this is a finitely generated topology, and you said rightly, passing to these stocks is like evaluating at a minimal open sets. So this means that all pre-sheaves for such topology are automatically sheaves.
no, I don't think this is, so I don't think this is correct. I think you still have to sheafify, but what is really nice is that since you are so you know that if you sheafify, your stalks don't change. So you still know
Yes.
what is happening on the stalk, so on this maximal intersection. So those spaces don't change.
Yeah, so
But in principle, you might have to
you are,
sheafify.
you are defining something which you call a sheaf.
Mhm.
Okay, so the sheafification is like is because sheafification for rich topologies adds a lot
Absolutely.
to these evaluations at some basis or some minimal opens. Okay, but now we are not adding by this sheafifying.
So you're talking about the example here, or
Yes, if
so
you have
here-
this finitely generated topology.
So in this case here, you don't have
My
to.
question is your pre-sheaf, because actually you are defining a pre-sheaf by listing values of this functor on this generating opens. Okay, so is it automatic that then every pre-sheaf in this finitely generated topology must be a sheaf?
I don't think so. I don't think that in this case, every pre-sheaf is a sheaf. In this case here, so this is a pre-sheaf that is also a sheaf. So here, this is on the nose, you don't have to sheafify. In the other theorem that I showed you about OQG,
So every time you are checking simply this sheaf condition. You are testing it on.
No, so I'm not checking it every time since there are infinitely many examples, so I cannot do it.
Oh, I don't understand.
So here,
if you don't have a general result,
I have one.
you don't have.
I think I have one. So, let me
why
explain.
why you call these things, these pre-sheaves, sheaves?
Okay, let me explain. So
Yes.
here in this example, yeah, this pre-sheaf is automatically a sheaf. I don't have to do anything. I made a general statement that was about OQG. Let me go to it, which was actually so this one here, yeah. So here, what you are building are pre-sheaves. Those are pre-sheaves, and what you are doing, you have to sheafify those. Otherwise, you cannot say that those are sheaves. So what happens if you sheafify? I mean, crazy things might happen. As you say, this might grow, but you know that the stalks don't change. So we know what is happening on those maximal intersection, and it turns out it's everything that we need. Everything else, even though it might grow, we don't really care.
So my point is that in your definition of all these objects you call sheaves, sheafification must be added.
True.
From the scratch, because otherwise, why?
Absolutely. So let me apologize. So I was really short on time, so I couldn't say very much, but this would be
So now
one of the comments that
I understand
you
the
always
definition
sheafify.
at least.
Okay, thank you.
May I?
Yes.
I have two questions, and you are pointing to the right slide.
Well,
So here you have this nice technology of classical quantum sections and generating as open cover, but you are working in the realm of homogeneous spaces. Any chance of going beyond homogeneous spaces to like general principal bundles?
so this would mean you need a more general definition of quantum section that I don't have at the moment, and I cannot think of how to go more general as well.
Okay.
This I cannot answer.
Okay. Yeah. Fair enough. And the second question is, in your particular example where we had with this OQSL2 and when you had this parabolic group, I mean, oh yes, exactly this one. So is it obvious that when you take coaction invariance, you get this classical CP1?
Is it that you take coaction invariance? So you mean here that, for example, here, if you take the invariance here, that you get this?
Yeah.
Yes. So I mean, there's also something you have to check. So so here note that you can, or you should maybe understand this U as alpha minus 1 gamma, which you can easily see is an invariant element.
Okay.
And then
in fact, I wanted to ask a different question. So what happens when Q is equal to 1 in this case? What kind of a principal bundle you've got?
what happens if Q equals 1? Yes.
Yeah.
So let's see, do you
I
still
have
get-
SL2C, fine, fair enough, nice total space.
Yes, so
Do I really have a principal bundle?
should be, right? So it should give you something non-trivial, yeah?
But I don't see how CP1 comes out. But it can. Yeah, but is it?
So in fact, in algebraic geometry, it is a definition of a parabolic subgroup. It's such a subgroup that if you are dividing a reductive group by it, you obtain a projective variety. Okay.
Thanks for clarifying this. Yeah, thanks.
Okay, any more questions?
So maybe I will comment what Piotr pointed to, namely this homogeneity. It's not maybe about homogeneity, it's about this ORE condition, which is difficult here. So since you have the bunch of examples in which you can prove this ORE condition, then you can glue all this picture. Okay, so yeah, but the problem is, do we have such examples of such ORE systems outside the homogeneous real?
That's a good question. Yeah.
More questions? Okay, so let's see online. No, nobody. Okay, then we can thank the speaker again. And we stop for a coffee break. I stop the recording.
You just click power or yes.